Good morning everybody and welcome to my video. This is the first video I've ever made to explain airspace topics, so let me just briefly explain why I'm doing this. I've always felt that there's a need for a channel that explains airspace engineering in a more in-depth way than what is currently being done. So in short, I hope to present to you a full range of what a typical airspace engineer learns at university, everything from material science all the way to space systems engineering by posting regular videos to YouTube to make it more understandable and relatable than with the typical education. With this video, I'm testing the water, so to speak. If I'll get enough views, I'll continue posting videos on a regular basis. So, if you like the video, just give an indication by either subscribing, liking, or giving a comment like I would support a patron. Any other suggestions are very welcome as well. Alright, so let's get down to business. Today we're going to discuss a very basic concept in aerodynamics called lift. Lift is nothing more than the force that lets airplanes fly and take off. Of course, this may be a little bit of a simple way of saying it. In reality, things are a little bit more complicated than that, and the actual definition of lift is the force that acts on a body perpendicular to the oncoming flow. To make this a little bit more easy to understand, I've here drawn an airplane. The whole airplane, just like any other type of vessel, generates lift through the incoming air that flows over its body as it accelerates and maintains a high speed. The whole body of the aircraft generates lift, but this amount is neglectable in comparison with the amount of lift generated by its wings. So let's take a closer look at the wings, and especially a cross-section of the wing. Now, to make things easier, imagine air flows a lot like water would. On the top part, you have a beautiful bend that gently curves the air around the wing, creating little friction. As you can imagine, the air will exert a little pressure on the wing there. However, if you look at the bottom side, you can say that the curve is a little bit less gentle. It encounters a much more steep bend that pushes the air against the wing. This also implies that the air is moving slower and is pushing more against the wing. This force that pushes against the wing is made out of two elements. On the horizontal plane we have something called drag, which literally is the friction it has on the horizontal plane, and on the vertical axis we have the lift. Now we have an easy equation to calculate lift of a wing. The lift is, in Newton, half times the air density times velocity squared times the wing area of the particular wing times the lift coefficient. Now most of these variables may be very easily recognized, except for the last one. The lift coefficient is a function of the angle of the body towards the flow, its Reynolds number and its Mach number. And today we're not going to go into that. When you are asked to calculate the lift of an airplane, usually the lift coefficient is given. The other way around, it can also be that the lift force is given and that you are asked to calculate the lift coefficient, in which case you can recalibrate the equation to show how to calculate the relevant lift coefficient. If you don't know the lift coefficient or the lift force, what you always can do is go to airfoiltools.com, the link is in the description, and look up the relevant airfoil for your particular aircraft. Now, let's use this lift equation in a relevant example. And I think there's nothing more appropriate for the first video than to calculate the lift of the first aircraft, the Wright Flyer. So, to calculate the lift force of the Wright Flyer, we simply have to know the surface area of the Wright Flyer, and you can see. And to do this, we've simply looked up the measurements of the airplane and put them in the equation. I've also looked up the other specifications with regard to the Wright Flyer and filled them in. And as you can see, we're now arriving at a lift force of 1895.785 Newton, which roughly would equate to, let's say, somewhere in the vicinity of 170 kilos. So, Then in order for our Wright Flyer to fly, the lift that ought to be generated should be higher than the total empty weight of the airplane plus the weight of the pilot. And if we look at that equation, there is something interesting to be noted. Namely, the weight seems to be larger than the actual lift. And so our question would be, why doesn't our airplane fly? Or better asked, why did the Wright Flyer fly? If the lift was substantially lower than its weight, then it should not have taken off. And we now arrive at something that a lot of aerospace engineering students will go through in their first years. Sometimes you have an equation, you've checked all the parameters and you've checked them again, but you arrive at an answer that is not satisfactory, because in this case it doesn't or is not supposed to fly. So then we can have a discussion why or what happened that this airplane in this occasion did fly. Well, I have looked up several possibilities, and one of the larger possibilities is that there was a substantial wind on that day, averaging about 32 kilometers an hour, so that would have added to the velocity. And if you take note that the velocity was at that particular point 48 kilometers an hour plus, let's say, 32 kilometers an hour, then you would have a substantially higher lift. The other thing, but of course this comes with the downside, is that we have calculated the lift at an angle of attack of 0 degree. And what I mean is basically that the angle under which the wing is, as opposed to the flow, is 0 degree. When an airplane takes off, an angle also exists with regard to the wind and the wing. They could have done something similar, and that generates a large amount of lift, but reduces the amount of speed. So the speed in effect would also be lower. So technically you could fly at a lower speed but have a higher lift. And this is also what seemed to have happened here, because in the notes of the first flight, it is said that the airplane left the rail, but Wilbur pulled up too sharply and stalled, and came down 3.5 seconds with not much. 3.5 seconds later with not much damage. Well, stalling is exactly what happens if you would put the aircraft under a large angle. Basically, if it hits the air too steep, the flow over the wing collapses, and then behavior becomes unpredictable, and hence no lift is generated. And in this case, the Wright Flyer would basically fall vertically out of the sky. So these two arguments, one, that the angle of attack was different, and secondly, that there was a lot of wind on that day that helped increase the lift under the wing of the Wright Flyer, seems to be, for me, the most logical explanation of why the lift would be higher than in this particular example. However, feel free to comment below if you have any other ideas, or whether you see any mistakes in my equations. This might also be the case. Thank you for watching, and see you next time.